Welcome to today's lecture on ensemble classification. This is in continuation with our previous lecture, which was an introduction to classification, where we introduced two simple classification systems. One was a nearest neighbor classification system and another was a decision tree classification system. Today what we'll do is look at what is called as ensemble classification, which essentially is putting together these simpler classifiers that we saw from last lecture and obtain a performance that's better than them just working individually. So we'll find smart ways to join simple classifiers and obtain better performance overall for various classification tasks. So let's dive in, and before actually we get started, just a quick reminder what we saw last week in terms of what it means formally to do a classification problem. So what we have usually is a set of classes, so omega 1 to omega k. So these are the different classes of the objects that we are interested in finding out what's there in the image. And for our image itself, or whatever data it is, we have a feature vector E. And the goal of a classification system is to come up with a function f that maps our feature vector E to a class C. So let's take the most important example out there to classify cats and dogs, right? So for example, given an image, you want to figure out what are the cats and what are the dogs. And a feature could be you record the color of the eyes of the animal that's there. So you don't know at this point whether it's a cat or a dog, and you want to figure out that it's a cat or a dog. You see if it has a tail or not. If it has a tail, what's the color, and so on. So these, to say, are the features E, which represent your input space. Of course, you could also work at a much more lower level, in the sense that you put in an image and each pixel of whatever is there in the image is the animal that you want to classify or so on. And our goal here would be to come up with that f, which given your image or given the features is able to say whether it's a cat or a dog. And we also said last time that the problem that we focused on was one where you only had two classes, so omega 1 and omega 2. In this case, for example, cat, and omega 1 is cat, omega 2 is dog. Or in general, omega 1 is the main class that you're interested in, and omega 2 is everything else apart from that particular object that you're interested in. And this leads us to the binary classification problem. So we'll kind of focus, also keep our focus on the binary classification problem in this lecture as well. But essentially, whatever techniques we learn for the binary classifier also kind of extends to the classification problem where you have k unknown class or k classes in your image or in your data, right? So let's then get started or get introduced to what really ensemble method mean and why are ensemble methods necessary or used in practice. So essentially, the key idea when I say an ensemble method is that you have certain classifiers with some performance. So you have a nearest neighbor classifier with some performance, a decision tree classifier with some performance. And the question that we ask today is, can we actually combine these classifiers and obtain a better performance than if you were just to use them individually? So this is the goal that the ensemble methods try to take advantage of. And in particular, we will look into two such approaches. One is called as bagging and the other is boosting. And we'll see these are kind of smart ways in which you can use your training data set to come out with a method to put these simpler classifiers together and get a better performance overall. And these are kind of just two ways in which that you can do this, and we'll see the details as we go through the lecture. Okay, let's start with the first one, what is called as bagging, or more technically, let's say it's called as bootstrap aggregation, but bagging is a nicer word, so let's stick to bagging. And here, the idea is actually quite simple. So what you have is your training set. So like we saw last time, your training set is nothing but a collection. So you have n of these guys. It's a collection of a tuple, where E is the feature that describes the object and omega is the class of that object. So this is our training set where we have, in this case, n examples. So we have n vectors, and for each vector we know what the actual ground truth class of that vector is. And last time what we did was to use this training set and then train our classifier based on this example. So we would come up with that classifier that best explains the examples in our training set. But today or at least what the bagging approach does, is first it breaks up into B smaller data sets. So here this number is NB. So you take your big data sets, for example, your N is 100, you take your 100 example data set and then break it down into B small parts, let's say 5 small parts, and therefore you will have 20 data points each. And then what you do is to train a classifier for each one of those smaller data sets. So you will end up with F1 for N1 for the first part of the data set. Similarly, for the second part of the data set, you will end up with F2, and so on. For the bth data set, you will end up with the FB. So now, instead of having just one classifier which is trained on the entire data set, we end up with B classifiers which are trained on smaller data sets. And the goal would then be to take that decision, which is kind of the majority vote. So for example, F1 says it's a cat, F2 says it's a cat, and FB says it's a dog, just for example. Then since cat has 2 votes versus dog has 1 vote, we say, okay, it's a cat. So essentially the idea here is that the decision that would be taken by multiple classifiers would be more robust to noise and more robust in general to also errors that you might have in your training data set, and you would end up with a performance that's usually a little bit better than just using any one of these classifiers, that is F1, F2 and so on. So we'll really dive into the details later on, but before doing that, just let's get a quick introduction to boosting as well. So boosting is another technique in which we can combine these F1s to FBs, but it's done in a slightly different way. Here, what you do is that instead of breaking down your big data sets into B small chunks, what you do here is you kind of train in an incremental manner. And what I mean with incremental manner is the following. So first, what you do is take your entire data set, then train a classifier F1 on this data set. Your classifier will make some mistakes. The idea then is to figure out what a good F2 would be that makes less number of mistakes on these examples that you misclassified the previous time. So essentially you focus more on the examples where you made errors in the previous time. And this way you end up with B different classification system, each of which tries to correct the errors from the previous classifier. In this way you end up with a bunch of classifiers, again B, and then instead of taking a direct majority vote like we did with the bagging approach, what we have here is also a concept of weights. And we'll see that these weights are related to the number of examples that the particular classifier, say F1, actually makes mistakes with. And then combining these two pieces of information, you can end up with a combined classifier, which is a boosted classifier, so to say, which is often much better in terms of precision and recall, and gives you an overall just more robust performance. Okay, so this was just to give you a very quick introduction into what we are going to look in this lecture. And now we kind of dive into the weeds, so to find out the details of exactly how this is going to work. And in particular, we'll focus on one variety of bagging approach, which here is done using decision trees. And the logic here is that since you have a bunch of trees, they form a forest, and therefore what you have is a random forest classifier, since you have these multiple decision trees acting in some sense together to decide whether a particular feature vector is omega 1 or omega 2 or omega k in general. Right. So this is the same slide like we saw before. The idea is to combine individual classifiers F1 to FB, which have been trained on parts of these data sets. Right. So given this, the question then becomes actually how do we realize this, right? So if you remember from the previous lecture, we had a decision tree. So this is how you can represent a decision tree. Essentially, a quick recap would be if you have a feature vector which goes on the top, the goal is to end up in one of these leaf nodes, and the class of that leaf node is the answer of your classifier. What is the class of that image or of that data point? And essentially now what we do is train multiple of these decision trees and then make a majority vote to figure out the actual class of the input. Right. So so you see again a really quick, like 1 minute recap into the decision trees. So the way we had formed the decision trees was to ask a question at each level, such that it splits our input space with the minimum ambiguity in the child nodes, in the sense that you try to ask the question at each level. So in this case, the question is x1 greater than the threshold W10? And then the way you ask these questions is such that the elements or the training examples which fall into these two spaces, less than 10 and greater than 10, is such that you have a maximum separation that you have. And if you remember, we had a couple of metrics to measure this. We had the entropy metric and the Gini index metric to do this. And this way you can actually come up with one decision tree. Right, so this also falls into the popular divide and conquer paradigm, where you ask questions each time and you kind of divide your input space such that you map, okay, this part of the input space refers to omega 1 class, this part of the input space refers to omega 2, and so on. And we had seen this example also before, where we want to separate these circles from these squares. So whatever, you can say these circles are the cats and the squares are the dogs, and essentially you want to end up with these decision boundaries, which is nothing but a representation of what you saw in the tree. So what this node corresponds to, x1 greater than W10, is it's breaking our input space into two paths. So since this is our x1 feature axis, you have paths which is left of x1 and paths which are right of x1. And this is exactly what you see here. If x1 is greater than W10, then you go into this branch, and then you check the other dimension. You then check, is x2 greater than W20? So if the answer is yes to both these questions, so which means that if x1 is greater than W10 and x2 is greater than W20, this is the part of the space which corresponds to omega 2. Whereas on the other branches of this tree, you reach to the regions which the circles occupy. So in this way, by asking simple questions, you divide your input space and you're able to classify your training examples. So this is how one tree works. Now the question is, how do I combine many different trees, or how does this bagging approach work? And essentially what we do is we randomly split the training data. Right? So what we do is take this big training data set, where actually each row of this set is, or of this matrix, is one training example. So this E11 to E1D is nothing but this vector E, which describes your input image or input data, and omega 1 is the training label corresponding to that particular vector. And in our case, we would have, in this case as it's shown, we have M1 examples, and by picking up different rows of this matrix would essentially mean you are splitting that matrix into smaller parts. So in this case, let's say we picked up the 5th row, the 9th row, and the last row. So this is one subset from our original training data set that we made, and we do this B times. So essentially we end up with B different training splits. So this is only the first kind of split that we do. Next, what we do is to add a little bit more randomness into the process. We actually split column wise. What this means is that each column here corresponds to some feature element of that data point, right? So maybe this corresponds to the color of the eye. Maybe this row corresponds to if it has a tail or not. So each of the columns correspond to a feature point. And what we now want to do is to kind of create a data set where we remove some of these rows. So randomly choose different columns that you want to remove and remove them. And then you end up with now a new set of broken down examples that you have, or broken down training sets that you have. And the intuition behind doing this is that you want to really find out which features are the most distinctive ones. So which are the ones which are helping actually to classify the space. And this way, by splitting both across examples and across features, we create a good mix of training sets on which we can train these smaller smaller classifiers F1 to FB. And then essentially we just pack them all together. On each of this training set, we train a classifier, put them all together, and they give you your forest. Right? And then, like we said before, each of your tree in the forest makes a decision, and say if you have whatever n trees, then you take a majority vote amongst these n trees, and then you end up with one decision saying, okay, given the data point or given the new example, this is my class. So this is the whole story behind the random forest classification. And also in principle, if you think of this idea, you can extend it to other classifiers. Nobody is stopping us to replace this decision tree with, for example, a support vector machine based system or some other system that you might develop, or your favorite neural network or whatever. Because in the end, what the bagging does is just provides an idea of how you can combine multiple classifiers and say something that's a bit more robust than each individual one would do. In this case, of course, it's called a random forest since it's built from a tree, but the principle of bagging is more general, and you could mix and match different kinds of classifiers as well. And this results, the fact that we do this process of splitting the data sets into smaller chunks actually has a natural effect that reduces overfitting. Otherwise, if you just have one big data set, and if you have a system that's strong enough to fit all the examples that you see, or it has enough parameters to explain all the examples that you see, you might just overfit to the training data set, whereas you will perform poorly on the test and the validation data set. So by breaking up these data sets into smaller parts, you reduce the risk of all of your candidates to overfit. Now, since you've put your so to say eggs in different basket, not all of them will overfit. Maybe some of them underfit, maybe some of them overfit, and some of them just fit perfectly. So you have a much better mix of your classifiers, which with the hope essentially that you would get out with performance on new examples which is better than any one, or which is better than just using one big training data set. And in practice, it has been seen that by doing this splitting, you can actually end up with better accuracy than actually using a much bigger or a much potent classification system with a large number of parameters. What's also nice with this is that you have the chance to parallelize, because each tree essentially is making an individual decision. So while making the inference, so while actually, say once you're done with the training, while making the inference, you can ask, let's say if you have 100 trees, each of them can run on one thread on your CPU or on your GPU, and then the only time you need them all to be synchronized is at the end where you make a majority vote. So this way you can actually parallelize the running time, but also you can parallelize the training, because if you see, once you split your data sets, the individual training of each classifier is independent of every other one. So also during the training process is something you can parallelize. So this method yields to very simple parallelization. Therefore, you would find very accurate, very fast and accurate implementations used across systems. And one such example that you might have actually used is the body part classification system that's used in the Kinect, or at least was used in the Kinect at some point. And what they did in this example was to actually figure out what different body parts are. So here you see different colors overlaid on a human, and they want to figure out what an arm is, what a leg is, and so on. And based on this, they have some application where you play a game or you interact with a virtual environment and so on. And this system was built on a random forest kind of a system where they had over 1 million test images, and using this highly optimized GPU training, they were able to train this whole 1 million example system in a day. And this was something that's in the end actually run real time on the Kinect itself. So in the end, you can come up with quite effective and fast algorithms that actually run on embedded systems like the Xbox here, as it's shown. So this is just one example of where you could use random forest, but it's just one example. There's just infinite number of applications that you could build with this. Right? So a quick summary before we move to boosting. So in random forest, we combine a bunch of decision trees to make a decision forest, and each tree is learned on a subsample data set where this subsampling occurs both in terms of the number of examples you use and also the properties of each feature that you use to train that particular example. And the whole idea of doing this is to avoid overfitting and to kind of figure out those sets of classifiers which use different parts of the feature vector. So for example, taking again this cat and dog example, maybe you want your classifiers to, let's say the classifier F3 to focus only on the tail, whereas you want the classifier F5 to focus on the eyes and so on. So this way, by eliminating the other columns of your feature vector, you focus on these elements and see, okay, are these elements distinctive enough to give me the performance that I want? And in practice, it's been seen that it's quite easy to implement this, because essentially all you need is to take a bunch of decision trees and make a majority vote. So in terms of implementation also, it's something that's easy to be extended to different classification systems that are out there and not just decision trees in particular. Okay, I hope this gave a good overview of what a random forest based classifier system looks like. And now we would go to the other technique that we talked about, which is boosting, how to make the classifications more effective by combining them in another manner. And AdaBoost is just one flavor of this boosting algorithm. It's one of the most popular ones. So we'll go through the various steps that are involved in AdaBoost and in what applications they're actually used in practice. Right, so again, so this is a quick overview of what I said before. What is boosting? So in boosting, essentially you want to learn your classifiers in an incremental manner. And the main idea here is you want to learn the classifiers incrementally such that they improve on the mistakes that you made in the previous step. So if F1 makes mistakes, for example, 7, 10, 12, then my goal is to come out with an F2 which does well for those 3 examples. And the idea is that by doing this recursively, we end up with a bunch of features which explain different examples in your training set well. And the goal would then be to merge them using some weighting factor, which uses your error metrics for that classifier, and come out with a combined decision, which hopefully in the end is more robust than any one of them individually. Right, so a couple of terms that you would come across when you read about AdaBoost, let's say in the literature, and these terms are what are called as inaccurate rules or weak classifiers. So these are nothing but individual decision trees. So if you go to the previous example, these smaller decision trees are known as these weak classifiers, but in principle, this could be any classifiers which by themselves do not meet, let's say, your requirement of accuracy for the application that you have. So this is not good enough, but still something that gives okay classification accuracy. Of course, what means okay here is that it should be better than 0.5, right? Because if you have 0.5, it means you're guessing randomly. So it should be at least 0.6, 0.7, something like this. So you're looking for classifiers which are not super great, but they're good enough to be better than random guesses. And we want to come out with an accurate rule, capital H of X, which would combine these smaller H of X's to bring together their individual gains, so to say, and combine them in a proper manner. Right, so the most popular kind of algorithm which is in this category of boosting is what is called as AdaBoost. Actually, it's quite an old algorithm from the 90s, but it's something that's still used in practice because it gives really good performance, and it's also, so to say, agnostic of your individual classifiers that you use. So you might come up with new classifiers, but nobody is stopping you from using AdaBoost to actually bring those together into one system. And that's why, although it's quite an old one, it's still super popular. And like I said before, the goal would be to have a weighted voting scheme where we want to come out with this h of x, so this capital H of x, which here is defined as the sign of a function f of x. So here the function sign essentially is just a mapping between what value you get here to a +1 or a -1. And in this case, this is how usually AdaBoost literature refers to this capital H, and that's why we explain it in this way. Essentially, +1 can be mapped to omega-1 class, -1 can be mapped to omega-2 class. And the function in here, f of x, is nothing but this weighted combination of your individual small weak classifiers. So in this case, you have L weak classifiers, and you have alpha L's, which are the weights for these individual classifiers. And then you compute a scalar value, which would be a weighted product of these of basically alpha L times h of L, and then you put it in this function, which then corresponds to the decision that your overall boosted classifier takes in the end. So here the notation changed slightly from the previous slides. We were using W's here and F's here, but to be consistent with most literature which is in boosting background, they end up using this notation. Therefore, we'll follow this notation from here on. And you might ask, why is AdaBoost interesting? So in some ways, what by combining these weighted combinations of individual classifiers you do, essentially you are figuring out what the best features are to classify your input space. And since it's done in a way that you classify wrong examples incrementally, you figure out really which are the ones which features are the ones which are really determining the classification output. There may be your feature vector E may consist of, let's say, 200 elements, but maybe there are just 4 which are really critical to make the decision. And by doing this weighting process, the AdaBoost is essentially figuring out which are the best features that are out there. And we'll also see in the next slides, the AdaBoost also gives us a way to figure out what are the best thresholds for each of these weak classifiers. So if you think of a decision tree, you need to choose a threshold to say, if my feature vector is greater than this value, then it's a positive example. If it's less, it's a negative example. But somebody has to say where you should choose that threshold, and this is what also AdaBoost provides some hints at least to figure them out. And in the end, it gives us a formula, so to say, to combine these individual decisions into a final decision. Right. Some of properties that are more interesting, let's say from a theoretical point of view at least, is that AdaBoost is a non-linear classifier. What this means that if your input space has examples which can't be separated using just straight lines, then you actually need some kind of classification system which has the ability to kind of curve around the examples and not just have straight lines to do this. And the way actually AdaBoost does this by using decision trees, which is the example we will see, is it kind of segments your input space quite in a quite smart way to come out with regions which have features falling from one class and so on. And this is one way that AdaBoost deals with the fact that your input space is not linearly classifiable by any one of your weak classifier, but as a combination of all these individual weak classifiers, you're able to obtain this nonlinear division of your input space, which is kind of required in most real-world situations. They're not linearly separable. And what also happens as a property, kind of a side property, is that it generalizes well to new examples. And the way this happens is that since it has to take care of making sure that there are fewer wrongly classified training examples each time in its process, it tries not to overfit to just those examples, but takes into account that I should not make more mistakes by moving my decision boundary a lot. And this way what you end up with is a property that you maximize the margin. So you kind of have your decision boundaries which are are kind of equally far away from the positive and the negative examples, and they're not too close to one or the other ones. A property which is kind of similar to what you would get if you use a support vector machine, and in the support vector machine the actual optimization function that's there is to maximize the margin, and AdaBoost through this combination kind of gets this generalization so to say for free as a side product of the procedure that it follows. And again, it's an easy process to implement, since you can kind of treat your individual weak classifiers almost as black boxes and then find a way to merge them together to obtain performance gains, which is often 10 percentage points or more in practical applications. Right. And as a prerequisite, what you need you need these small h of x's, which are of course better than random guesses. And once you have them, that's all basically what you need to run an AdaBoost algorithm to combine these smaller decision trees, so to say. And in this lecture, we'll kind of focus on one of these methods, so to say, what is called as a decision stump. Essentially, decision stump is nothing but a decision tree with just the first level. So you don't ask multiple questions, you just ask one question, and that is your classifier. So it's like a dumbed down version of a decision tree. One question classifier. If it's to the right of this threshold, you're a cat. If you're to the left, it's a dog. And we will see actually an example where we use these decision stumps to come out with a classifier which is actually really effective in explaining new examples, but also making sure that your training space is well explained. Of course, we can also use decision trees as individual h of x's, so the weak classifiers. This, of course, makes the individual training a bit more complex, but overall, AdaBoost will still support combining multiple decision trees. And you can also think of incorporating support vector machines there. Or in principle, you can also make a mix of these different classifiers that you have there, and the AdaBoost will come out with a proper weighing function for each of these classifiers, which will then tell you how to merge the decisions from individual classification systems. So a quick introduction to what a decision stump is. A stump is, it's a trivial decision tree with one level only, and at least formally we note it with this h of x j theta. So it might look a bit complex, but essentially what is happening is a decision stump in 2D is nothing but a straight line. Right? So it's this line here, and what the decision stump says is that if you're to the right, you are a blue example. If you're to the left, you are a red example. And the theta is the threshold which gives you different decision trees, so to say, or decision stumps in this case. So if you say move this somewhere here and you have a new line here, then you would say everything to the left is a red one and everything to the right is a blue one. But of course, then you would be making a mistake with this example that's sitting down here. So this line essentially translates to this formula here, which says, okay, this is the formula for a single decision stump. And then you say the class is +1 if the value of that axis of your feature vector is greater than some threshold theta. So you see these PJs here to kind of jump between left and right. So for example, you can have a decision stump which says everything to the right is a positive example and everything to the left is a negative one. But by setting PJ to -1, you can flip it. You can say everything to the right is now a -1 and everything to the left is a positive one. So just one more decision stump that's there by flipping this symbol. It's for mathematical convenience here. And that's about it. So now the goal would be, can I use this decision stumps and then put them together to get something that's better? Like I said, so what you also have in practice is your decision would be taken over multiple axes, right? So here, this is a decision stump on the feature vector x1. But similarly, you can also think of an axis or of a line which goes like this, and this would be x2. And in principle, we want that decision stump which explains best the data given the current situation. We don't care whether it's vertical or whether it's horizontal. We want the best of whatever we can get there. And like I said, this plus or minus 1 would give you this mirroring effect in terms of the class that it predicts. Now we need a way to actually train this decision stump itself, which essentially means where does my theta lie such that my decision stump best explains my data points that is there. And the way you do this is through this formula or through this minimization procedure. It might look a bit complicated, but it's really easy. So what this says is that once you have a decision stump H, you take in your data vector that you have, and then you have a prediction omega t. If the prediction of your h of x, so this is your prediction, if it does not match the actual ground truth label, because this is still the training phase, you add them up. So this I is nothing but an indicator function, which is basically 1 if the condition inside is true. So what this whole thing here is doing is just a fancy way of adding up your mistakes. Right? So this whole guy is saying how many mistakes that I made. And these mistakes can be false positives or true negatives. So the things that you misclassifying properly or the examples that you misclassified. So these are the two errors that we also saw in the previous lecture. And this is just adding them up. And this the W of t is actually weighing these errors, because we'll see in the AdaBoost procedure that not all examples are the same. So we will now attach weights to each examples, and we want to make sure that we reduce the errors for those examples which are more important, and therefore we have this weighted error. And therefore now the whole story of training a decision stump means you need to figure out where do I put these dividing line such that I minimize this optimization function that's given here. And if you see, we have another term which we need to estimate, which is the j, which in this case is which axis. So here j is 1 or 2. So you can either put lines like this or lines like this. So it's answering the question which feature or which column of your feature do you want to use to make the next decision in the overall boosting procedure. So at each step when I train a decision stump, I need to find out which is the threshold and which is the dimension along which I am cutting the space. So these are the two things that I want to find out when I'm actually training a decision stump. And if you look at this training process a bit more graphically, a really simple way of thinking of this training process would be, let's say my x1 feature vector varies between 0 and 10. And all I do is move this vertical line along this axis, and at each point, let's say I move 0.1, so I move from 0 to 0.1, I make this calculation up here, I will get a certain number of errors, right? And I do this for every single discretized space that I have here, and I get scores for each one of those vertical lines that I have. And then I want to choose that one which is the minimum most one. Then you repeat this kind of thing on the other axis, since we also have to choose the correct axis. So you kind of sweep over this axis, you sweep over this axis, and find that theta which minimizes your overall error. So in the first iteration, when all the examples are equally important, you can assume this weight to be 1. But in the next round, when you choose the second decision tree, you change this weights based on your previous experience. So what you do is you give more weights to the examples that were wrong in the first iteration, and therefore this weighted error would change each time. And this is the whole idea that the boosting actually exploits. Right. So if you were not happy with the graphical representation, this is an algorithmic representation of what we saw in this slide. And essentially what it says is the same. So you have j dimensions of your input feature space. You loop over each of those dimensions. And then for each of the dimension, you basically fix a threshold theta j, compute the error using this formula that we saw here. So this fancy looking formula here. And then in the end, you do it over your entire range that makes sense, and then choose that theta star and j star, which will minimize this error given here. So it's quite straightforward, couple of for loops, and then with this you can basically train your decision stump. But when you train a decision stump, what you're doing is you're training the small h of x, right? We still don't know how to get the capital h of x, which is the combined classifier. And this is what the AdaBoost algorithm gives you the recipe for, so to say. Again, if you look from the top, the input is the whole training data set that you have here. So you have t elements in your training examples, or t training examples, and you initialize all of them to have the same weights. And here we initialize them as 1 by t because we want to make sure that the weights add up to 1. And instead of giving weight 1 to all examples, we just give 1 over t to each example. And then what you do is, first, let's say you choose a limit on the number of classifiers that you want. In this case, it's capital L. So I say I want 10 weak classifiers, and I'm happy with 10 weak classifiers. This is again a hyperparameter you can play with. You can go for 100, 1000, depending on your application. And then what you do is, for each of those classifiers, you first train them. So in the example that I just talked about, it was this decision stump. So you train a decision stump, which would be h of x. Then training means to figure out this theta and j for that decision stump. And then you kind of characterize how good that particular classifier was through this score that we had computed before. So the smaller the score, the better is that classifier, because the smaller is the number of errors that this classifier is making. And then AdaBoost actually suggests a formula for what is called as a voting weight. So each of these classifier would have a weight, and it's like a vote. And at the beginning, kind of all of the examples, so to say, or all of the classifiers would have the same weight. But the whole point of using AdaBoost is to have a voting power that's weighted such that you kind of have in the end a combined performance that's better than the individual ones. And the formula that the AdaBoost suggests is this one here, which is nothing but 1/2 times log over 1 minus this error that we described here, divided by the error that we have here. We'll see exactly what this means, but essentially this maps to the fact that if you have a higher error, that would lead to a lower weighting weight in your final decision that you will make. So also makes sense just intuitively. If you make fewer errors in your as an individual classifier, you mean more to me in the group than other ones which make more errors. Right? And then what we now have to do is also recompute the weight of individual training examples. So here we have to be careful. So when I say the voting weight, this is the weight that I give to each individual classifier. So H1, H2, H3. And when I talk about recomputing weights here I mean basically what is the weight for each individual training example. And for example, a case at the extreme would be, let's say if I have 10 examples and 9 of them are so easy to classify that they have weights of, let's say, 0.01. Whereas the other example is so important that I don't want to make a mistake that could have whatever 0.91 weight or something like this. So the idea is of weighting those examples which you usually make more errors with to have greater weight, such that you force the newer classifier to make sure that this example which is difficult to classify is definitely classified correctly. So this is the whole idea that you have, and in the end you combine this in basically a weighted sum way to get your decision. So this is the overall, let's say, the schema for implementing a AdaBoost algorithm, and you can kind of replace these, or these are quite general. Say whenever we say weak classifiers, you can put in any classifier in there, because in the end all you need from that classifier as an output is a metric which says how good did this classifier work. It doesn't really care so much about how it does this classification. It's more about how you or how good was that classifier and how good was it in terms of specific examples that is there. So that's the important message there. So don't think that this AdaBoost only works for decision stumps, but it would work for any classifier that you like. And just to understand a bit more how this voting weight works, essentially this formula is such that you have a higher weight if your error that your classifier makes is little. And conversely speaking, let's say if your error rate of your classifier is 0.5, which means that it does half of the the examples wrong, which is like random guessing, right? So when you are random guessing, basically this says, if you plug it into this formula, you have 1 minus 0.5 over 0.5, which is 0.5 over 0.51, and log of 1 is 0, and that's what you see here. So the weight for a random guess is 0. So if you come up with a random guess classifier, the AdaBoost will say, I don't care what this classifier says. Whereas as soon as you keep improving, you get higher weights. And so the idea is to have, or to come up with those weak classifiers which run more to the left of the, left at least in this weighting space that you have. Right. The other weight that we had seen was the weight of the data point. Right. The weight of the data point has this kind of expression here. Again, don't worry that it looks a bit complicated. In the end, what is important is that this weight will be less than 1 if you have if your prediction matches with the actual ground truth, and it's greater than 1 which is otherwise. What essentially it is meaning is that you have this weight from the previous time step omega t or wt. If I make an error, which is this case, right? So my omega t is not the prediction. I actually want a number which is greater than 1. Right? So I want to give now more weightage to the data point which I made a mistake with in the previous time. So the way this weighting works is I push up the weights of those examples which are wrong and push down the ones which have been already correctly classified. And this ZL here is nothing but a term which makes sure that this WT at the end adds up to 1, because we always want the weights to add up to 1. So although the formula looks complicated, but essentially it's coming up with a way to increase the weight of the wrong examples and decrease the one of the right ones. And in principle, you can also come up with something very easy. So you say, I multiply with 2 every time I make a mistake, I divide by 2 every time I make a correct. So you would end up with a simpler looking formula, but would do roughly the same thing that this particular exponential decay formula does. Right? And with that, yeah, this is what exactly I said. So you want to increase the weights of the examples which have been misclassified versus the ones which have been correctly classified. And this is the, let's say, the core principle of AdaBoost. So you want to make sure that you have, or you give enough attention to the wrongly classified examples. And in machine learning literature, you would also come across what is sometimes called as a hard negative mining, which essentially means you take those examples which are really difficult to solve or difficult to classify properly and really train your systems for those really bad examples, and then you will anyways do well with the other easy examples. So it's a similar concept that the AdaBoost also exploits and brings together multiple classification systems. Right, and finally the h of x, which is actually the output of our AdaBoost classification system, would be this combination of your individual stuff with this alpha else. This alpha else is this voting weights that we had seen before, and then it's made in such a way that the answer would be either positive or negative. So this could end up being something like, say, 0.6. If it's 0.6, you check the sign of 0.6. Since it's greater than 0, it's 1, it's omega 1. If it's a negative number, it's omega 2, and so on. So this is just a mapping between the h of x, the capital H of x, to the actual class that you have, omega 1 and omega 2. Okay, all this is good, but let's actually see how this works for a real example visually. So we won't go through the calculations, but we will see visually how this whole process looks like. So let's say this is our space. You have pluses and you have the diamonds. So if you like cats and dogs, pluses are cats and diamonds are dogs. And now you want to really classify this space. And if you think of it, this space is not linearly classifiable. So you can't put one straight line anywhere such that you really have a good performance on the input space. So you need something a little bit more fancier or more complicated in general. And as you saw, each decision stump is nothing but a straight line. So what would the AdaBoost do is now combine those straight lines in a smart way to come up with a good breakage of, so to say, your input space. So let's say what happens in the first iteration, right? In the first iteration, you did your Stump training, and the decision Stump said, okay, choose this dimension, let's call it x1, and choose this particular decision boundary. And now this is the best I can do given one classifier. This is my start, right? What you then do is you evaluate how good is this classifier. As you can see, in this case, you make 4 errors on the right by misclassifying pluses as diamonds, right? And you see, okay, you make 4 different errors. Based on these errors, you can of course compute this weighted error, which is this big formula with the indicator function that we saw. And since it's the first iteration, all the examples are equally important, so the weights is just 1. And then you put in, of course, your other formula here. Yeah, the other formula here to get the actual voting weight for that classifier. And then in this case, it happens to be 1.39 is the voting weight that you get for this example. Now is the interesting part. Now you recompute the weights. You now saw from the last slide to now that some of the pluses have become bigger and the other pluses have become smaller. So let's see this again. So this is iteration 1, iteration 2, right? So these things have become bigger and these things have become smaller. Essentially because we had already classified these things as correctly, so now we can give them lesser importance. And these were the ones which we made mistakes with, so let's give them higher importance. And then you repeat this again, right? So you have in the second iteration, now you want a new decision Stump to do this. And now you see, okay, it really made sure that it did not make any errors with these other examples. Since you increased the weight for these examples, it was okay with making errors with these diamonds in here, so it's still making errors, but it really wants to make sure that it didn't make errors with this bigger weighted elements. So this is the way you kind of now dealt with these guys. But now, again, when you reweight, these guys become bigger because in the second iteration, you made more errors with these diamonds down here. So you can repeat this process again. Now since these diamonds are kind of bigger, you try to make sure that those diamonds are properly classified. And this is where you can repeat it, you can recompute the weights, and we do this a few times, so I'll just go over them slowly. And as the iterations increase, maybe the weights are no longer equally distributed, but that's the magic part of it, because you kind of make the weights of those examples really bigger, which are becoming more and more hard to explain. And as you go towards the end, you want to make sure that you explain them as well as you can. And in this case, I think we have iteration 5, in which we still make 1 error. Then we redo the weighting, so this guy gets more weight, so that we must now make this correct in the next iteration, and therefore this decision Stump was chosen, and so on and so forth. So we have 7, recompute, 8. Now we have reached a place where we are making 0 total errors in all. And in the end, what we can end up with is this kind of partition of the space where each individual decision Stump was not particularly great, but overall when put together, at least in this example, you are now able to break the space exactly into the regions which fall into the pluses and the diamonds. So this partition of the space is a non-trivial one. If you were to, for example, fit a polynomial, you would probably need to have a curve which goes like this around your examples to figure out this thing. And now what we have done is found out a rather simple way of putting together decision Stumps, which are nothing but a one question check, and come out with a fairly good partition of the input space. In this case, of course, it's a 2D example with few examples only, and therefore you could get a total training error of 0 in the training phase. But in practice, if you have thousands of examples, you might not end up with a 0 error, but you will end up with an error that's reasonable, and you need to choose this error in terms of your application. So for example, if you really strive always to have 0 error, you might break this space into so many partitions that you would overfit the data. So often you need to choose a threshold. Okay, if I get 90% accuracy, then I stop breaking up my space anymore, because if I do more, I'm probably overfitting. So this is one hyperparameter you still have to take care of, but overall you get a much more powerful classification system than just using individual decision stumps. And one of the most popular example that uses AdaBoost is this face detection algorithm by Viola Jones, which you probably might have come across in your studies. And although this is an algorithm from the 90s, it still performs as good as some of the most complicated neural networks that you find out there, simply by using these simple, what are called as the HAR features, and then combining them using an AdaBoost. You don't, of course, get the same accuracy as, let's say, a million parameter neural network, but still you get an accuracy which is really impressive for using simple 1-0 kind of classifiers, and to get something like this is really impressive. So before I finish, I give you a really quick summary on what we saw in terms of AdaBoost. So it's a way to combine multiple weak classifiers, and the take-home message in this AdaBoost or boosting in general is to make sure to incrementally choose those classifiers which classify your mistakes from the previous round correctly. And in this way, you're able to kind of make sure that these harder examples are explained over time. And in the end, you end up with a combination which is much better than any of the individual classifiers that you can come up with. And this algorithm was somehow proposed around 2001 and is still widely used in the classification community for various tasks. So with that, I come towards the end of this lecture, where basically I introduced in the last lecture essentially how to evaluate classifiers and what does it mean to generalize to new examples. So it should not just work, or your classification system should not just work on your training set, but work for examples that you haven't seen before. And we saw this concept in the part 1 of this lecture. And then today we saw how you can use the idea of bagging and boosting to combine these simpler classifiers into a more effective one. And finally, we saw the application using decision trees on what is called as the random forest, as well as the AdaBoost example that we saw at the end. And if you're still curious and hungry to learn more, these are two references which I would definitely recommend. This is like the classical reference for random forests. If you want to understand the math and the various derivations that are there, I highly recommend you to read the article here. And also, like last time, I would also encourage you to read the book from Alpayedin, which goes into many of the basics of machine learning, and in particular, bagging and boosting is something that's covered in chapter 17. With that, we come to the end of this lecture, and I hope it was fun and you learned something new here.